to channel Knowledge of Friends. Subscribe to our channel and click the bell icon for the latest update. Today we're going to start with discussing about chemistry for class 11, that is your class 31st. We had done 30th class in the last session where we will discuss physical property of the group 15 element, that is the carbon family. In today's class, in 31st class, we'll start discussing about the chemical properties that we have. This is your oxidation state oxidation state and trends in chemical reactivity. Then we'll discuss on the same. We have a parts for reactivity towards oxygen, reactivity towards water, and reactivity towards halogen. Then after completing the chemical properties, we'll start discussing about important trends and anomalous behavior of the carbon. So let's go for the same. Before starting with the same, it's a huge request to all the viewers to please go ahead with like, share and subscribe so that many and maximum people can get the information at once, and you can also enjoy the video as well. So let's go for it. So chemical properties. So chemical properties, first we'll discuss about the oxidation state. And trends in chemical reactivity. So in chemical properties, where the oxidation states and trends in the chemical reactivity, here the group 14 elements have 4 electrons in outermost shell. The common oxidation state exhibited by these elements are +4 and +2. That carbon also exhibits negative oxidation state. Since the sum of the first 4 ionization enthalpy is very high, compounds in +4 oxidation state that are generally covalent in nature. In heavier member, the tendency to show +2 oxidation state increases in the sequence germanium, then your another one, and that is the lead as well in the last. It is due to the inability of ns2 electron of a valence shell to participate in a bonding. The relative stabilities of these two oxidation state vary down the group. Carbon and silicon mostly show +4 oxidation state. Germanium forms stable compound in +4 state and only few compound in +2. Tin forms compound in both oxidation state, where SN in a +2 state in a reducing agent and lead compound in +2 state are stable, and in +4 state that are strong oxidizing agent. In tetravalent state, the number of electron around the central atom in a molecule, example like carbon in CCl4, is 8. Being electron precise molecule, they are normally not expected to act as electron acceptor and or electron donor species. Although the carbon cannot exceed its covalence more than 4 other elements of the group that can do so. It is because of the presence of d orbital in them. Due to this, their halides undergoes hydrolysis and have a tendency to form a complexes by accepting the electron pair from donor species. For example, the species like SiF6 2-, GeCl6 2-, and SNOH6 2- that exist where the hybridization of the central atom is sp3d2. For that, we have subcategory, which is your reactivity towards oxygen. In reactivity towards oxygen, here where all members when heated in oxygen form oxides. There are mainly two types of oxide, that is your monoxide and dioxide of the formula MO and MO2 respectively. SiO only exists at a high temperature, and oxides in the high oxidation state of element are generally more acidic than those in a lower oxidation state. The dioxide, which is CO2, SiO2 and GO2, are acidic, whereas SNO2 and PbO3 are amphoteric in nature. Among monoxide, carbon monoxide is neutral, geoxide is distinctly acidic, where SNO and PbO are amphoteric. Now we go for a question here, which is your select the members of group 14 that forms the most acidic oxide, is commonly found in +2 oxidation state, and the third is the used as semiconductor. So no problem, we'll go for it. The question we have for in terms of reactivity towards oxygen. Select the member of group 14 that the first we have forms the most acidic dioxide. The second they had asked you is commonly found in +2 oxidation state. The third is used as semiconductor. So let's go for it. For the first one, forms the most acidic dioxide, that is your carbon. And is commonly found in +2 oxidation state, that is lead. And the third is used as semiconductor, which is silicon and germanium. Now we go for the second category, that is we have is your reactivity towards water. The second category towards water. In terms of reactivity towards water here, which is your the carbon, silicon and germanium are not affected by water. Tin decomposes steam to form dioxide and dihydrogen gas, which will give Sn plus 2H2O. In the presence of heat, SnO2 plus 2H2, where lead is unaffected by water, probably because of the protective oxide film formation. The third we talk about for the reactivity towards halogen. In terms of towards reactivity towards halogen, these elements can form halides of formula MX2 and MX4, where X is your fluorine, chlorine and bromine and iodine. Except carbon, all the other members react directly with halogen under the suitable condition to form halide. Most of the MX4 are covalent in nature. The central metal atom in these halides undergo sp3 hybridization and the molecule is tetrahedral in shape. Exceptions are SNF4 and PbF4, which are ionic in nature. PbI does not exist because PbI bond initially formed during the reaction does not release enough energy to unpair 6s2 electron and excite one of them to the highest orbital to have a 4 unpaired electron around the lead atom. Heavier members, germanium and lead, are able to make the halides of formula mx2. Stability of dihalides increases down the group. Considering the thermal and the chemical stability, germanium X4 is more stable than germanium X2, whereas PbX2 is more than PbX4 except CCl4. Other tetrahalides are easily hydrolyzed by water because the central atom that can accommodate the lone pair of electron from oxygen atoms of water molecules in d orbitals. Hydrolysis that can be understood by taking the example of SiCl4. It undergoes the hydrolysis by the initially accepting the lone pair of electron from water molecules and d orbitals of silicon, finally leading to the formations of SiOH4, as that is I will draw for you all. So which has been Cl, 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 Cl plus H2 I have two lone pair. This one lone pair will go here. Okay. Also the reaction give SiCl, Cl, Cl, here it is OH. One lone pair has been gone, and in the presence of plus 3H2O and 3HCl minus 3HCl, it will give Si OH, 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 and OH. This is silicic acid. Now we go for the question here. Question is SiF6 minus is known as, whereas SiCl6 minus not give possible reasons here. Question is, this is the sixth question of this unit. SiF6 minus is known where as SiCl6 minus not give possible reason. So here for that, the main reasons are 6 large chlorides ion cannot be accommodated around Si4 plus due to the limitations of its size. The second is the interaction between the lone pair of the chloride ion and Si4 plus is not very strong. So just we write it down. The first reason is, the main reasons are first, 6 large chloride ions cannot be accommodated around Si4 plus due to limitation of its size. Second is interaction between lone pair of chloride, iron, and Si4 plus is not very strong. So now we go for another one, which is the important trends and anomalous behavior of carbon. Importance trends and anomalous behavior of carbon. So here in the same way, where like first member of the other group, carbon also differs from the rest of the members of its group. It is due to the smaller size, higher electronegativity, higher ionization enthalpy, and unavailability of d orbital. In carbon, only S and p orbitals are available for bonding, and therefore it is accommodated only 4 pairs of electron around it. This would limit the maximum covalence to 4, whereas the other members that can expand their covalence due to the presence of d orbital. Carbon also has a unique ability to form p-pi and p-pi multiple bond with itself and with other atoms of a small size of a higher electronegativity. For examples of the multiple bonding are carbon double bond carbon, carbon triple bond carbon, carbon just we have carbon double bond carbon, carbon triple bond carbon, carbon double bond oxygen, carbon double bond sulfur, double bond nitrogen, triple bond. Heavier elements do not form p-pi bonds because of their atomic orbital are too large and diffuses to have defective overlap. Carbon atoms have the tendency to link with one another through covalent bond to form chains and rings. This property is called catenary, and where this is because of carbon bond are very strong down to the group, and the size increases and electronegativity decreases, and thereby a tendency to show that catenation decreases. This is clearly seen from the bond enthalpy values, and the order of catenation is carbon is bigger than a silicon, then that is bigger than germanium, that is equals to lead as well, and the lead does not show catenation here. So due to the property of catenation, the p-pi bond formation, carbon is able to show allotropic form as well. So that all we'll discuss in the next coming class with the table we have, so that we'll discuss. So stay tuned with us, and please like, share and subscribe so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Other than that as well, we had discussed many of the topics related to it. You can go for it, you will figure it out and you will find it out there as well. And after that, in the next one class we'll discuss the table, as well as we'll discuss the allotropes of carbon, that is your diamond, graphite, fullerene, and uses of carbon, as well as all these things we are discussing in the more coming classes. So stay tuned with us, and please like, share and subscribe. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion in the comment box. Thank you.